Today we're going to continue to work in section 6.1, which is the law of signs, but today we're going to cover a special case which is called the ambiguous case. You can read these three if you want to pause the tape at this point, but I'm going to move to the next slide so we can get right into this. If you remember from yesterday and the video the night before, solving a triangle is what we're doing. We're doing these for oblique triangles that are triangles that do not have a right angle. We have such special cases. We can use the law of signs in three cases. If I have angle, angle, side, angle, or side, angle, side. These two cases are what we've worked on so far. Given two of the angles and one of the sides, use the law of signs to set up a proportion to solve for the missing parts. This one we haven't covered yet, and you have not had an example of this yet, the side-side angle. The angle in this case is not the included angle, and you're given two of the sides. This is the ambiguous case. So, let me show you why it's called the ambiguous case. If I take a look at what I've got here, I've got angle A in a triangle is 35 degrees, side B is 10, and then side A is going to be some length. I've actually started to draw my triangle here. I've drawn a 35-degree angle. I've got segment B here drawn as 10. And I've got this other side adjacent to A, which would be C, drawn here with an array because I don't know how long it's going to be. Angle C is going to be up here opposite the segment C, and then A is going to be over here somewhere. Well, one thing that can happen in this, and there's actually four cases when I have an acute angle given. The first case, A might be too short and not able to come down and hit on this third side. If that's the case, you don't have a triangle that can be formed, you can move on to the next problem. There's nothing really to solve at all. Second case, segment A might be just long enough to come down and hit perfectly on this other side at one point. In that case, what happens is you actually have a right triangle here, and you can use our trig ratios from before. A third situation that can happen is that segment A might be long enough to where it would come down and hit on that opposite side down here at this point. But if I draw a circle on here to help you visualize this a little bit better, there might be another possibility to draw the same length segment from point C up here to hit down on little side C. If you notice, these two segments are going to be congruent because they are sides, or they're a radii inside of a circle. And what I've actually done is formed two triangles here, both with a 35-degree angle. Here's this triangle. Okay, I've got this segment 10, this segment is 35, and I've got this segment length, whatever that would be. And I also have another triangle from A out to this point, up to this point, and back to A, where my angle's still 35 degrees, this segment's still 10, and this segment's still the same length as this one. So there's two triangles that can be formed in that case. The fourth thing that can happen with side A is it could be so long that it's going to come down and hit this opposite side so far over here that I cannot put that circle on here again to form a triangle inside, like over in here. That's so long. So there's four things that can happen. Well, how are we going to determine which of those four things is happening? Well, I'm going to show you that right now. If I look back at this, what I'm given initially, remember segment A could be too short. The minimum distance that A would need to be able to come down and hit on that other side would be this length right here. Well, it turns out that shortest or minimum distance is the altitude from point C up here down to side C. We call an altitude a height. So from the information that I'm given and the fact that now I have a right triangle here, I should be able to find the length of that altitude. How am I going to do that? I'm going to set up a sine ratio. I'm going to say the sine of 35 degrees is equal to h over 10. And when I solve for h by multiplying both sides of this equation by 10, I get an answer of 5.74. So if this initial A value was anything less than that H value, there would be no triangle that could be formed. If it's 3, that would never come down here and hit on this other side. If it's exactly 5.74, I could solve for the missing parts of that triangle. If that other side was longer than 5.74, okay, longer than 5.74, but less than 10, that's when I would have 2 triangles that could be formed. And if it's longer than 10, that's when I would have 1 triangle formed. So let me go back and clear some of this off and generalize this. Let me get this out of here if I can. Okay, so generalizing this. This angle, I'm just going to call angle A. This segment, I'm going to call B. And if I set up the same sine ratio, the sine of angle A is equal to, that's angle A, now not 35 degrees, H over side B. And I multiply both sides by B. H ends up being equal to B times the sine of A. And that's what I'm going to make the comparison of little a to. If little a is smaller than that value, if little a is less than H, there's no triangles that can be formed. If little a is exactly the same length as H, if little a is equal to H, there's 1 triangle that can be formed. If little a is longer than H, but less than 10, well wait, we didn't call that 10 anymore, we call that B. So what I'm going to say is, little a is greater than H and less than B. There's 2 triangles that can be formed. And that's what makes this the ambiguous case, because you'd have to solve for both of those. The other case is that A ends up being greater than B, and that's that case where that triangle's formed way out in here, and again there would be 1 triangle that's formed. Things change a little bit when you deal with an obtuse triangle. Here's a table to kind of summarize this all again. You can see what I just covered again here at the top, the acutes. With an obtuse angle, it's much easier. Okay, if I give you angle alpha here and little b and the side opposite, if this little a, side A, is not longer than b, it's not going to come down and hit on this other side. So if the side opposite the angle given is less than the other side, no triangle can be formed. If it's an obtuse and that side is longer, there's 1 triangle to be formed. There's no ambiguous case there. You just got to see if a triangle can be formed first. Okay, on my first 3 examples here, I'm just going to see how many triangles can be formed. So here's what I'm given. I'm given A is 76 degrees, B is 20, A is 18. So I want to find the H value so I can determine if it's going to be 0, 1, or 2 triangles. So the 2 I'm going to use in the formula are these 2. The side that's opposite the angle is going to be what I'm going to compare to. So I'm going to take 20 times the sine of 76 degrees. And when I multiply that out, I get 19.4. Then in comparing the H and the A value, A is 18, H is 19.4, A is less than H, 18 is less than 19.4. If A is less than H, no triangles can be formed, so 0 triangles. In example 2, I've got an obtuse triangle, I've got a 110 degree angle, so I'm going to draw a quick picture to represent that. So there's 110 degrees right here, that's angle C. Segment C is going to be opposite. Segment A is going to be my adjacent side here, that's 200. If the side that's opposite the angle is not longer than the other side, and that's the case here, which this is 125, it's not longer than 200, there's no triangles that can be formed. So 0 triangles can be formed on number 2 as well. Okay, here's example number 3. Again, I need to find my h value. H is going to equal 12.8, which is your b value, times the sine of A, which is 58 degrees. And calculating that, I end up with an h value of 10.8. So as you look at this, 10.8 is my h value. I've got my a and my b value. My a value of 11.4 is between the h value and the b value. If that's the case, I end up with two triangles that are going to be formed. I'm actually going to go ahead and solve this and find both sets of solutions in the next example. So here you go. Same situation, same triangle, same given information. I know I have two triangles that can be formed. So let me go ahead and solve this using the law of sines. I know this angle is 58. I know this segment is 11.4. This segment is 12.8. Using the law of sines, I'm going to find angle B first. Remember, the law of sines is the sine of an angle, so I'm going to put the sine of 58 over the side opposite, which would be 11.4, is going to equal the sine of angle B over the side opposite, which is 12.8. If I multiply both sides by 12.8, I clear my fraction on the right. Calculating the left-hand side gives me 0.9522 is equal to the sine of B. And taking the inverse sine of both sides gives me angle B is equal to 72.2 degrees. Now that I have angle A and B, I can find angle C by subtracting both from 180, which gives me 49.8 for angle C. Now to find side little c, which would be this side over here, I'm going to use the law of sines again. I'm going to set up my ratio as the sine of 58. Actually, I'm going to put that in my denominator. Underneath, 11.4 is equal to the little c that I'm looking for over the sine of 49.8. Multiplying both sides both of this proportion by the sine of 49.8, I get side C is equal to 10.3. Now that's my first of two solutions. I'm going to try to show you real quickly how to find the other set of the other triangle, so the other set of answers. Again, I put a circle on here. Here's my 11.4. Here's the second triangle that can actually be formed. I took out the circle to help you see it a little bit. You've got the red triangle that's over here. I've called this now B prime, this C prime, this is still A. It's still 58 degrees. You can see my little skinny red triangle over here. That's what I'm trying to find, angle B prime. Well, it turns out what ends up happening over here to the right is this is an isosceles triangle. I'm using the one I've actually already found and putting this other segment in here, and I've already found angle B in this triangle. From the previous slide, if you remember, that angle is 72.2 degrees. Now, what you've got in here, this blue triangle, is an isosceles triangle. Isosceles triangle theorem states that if you have two sides of a triangle that are congruent, the angles opposite must also be congruent. So this angle over here must be 72.2 degrees as well. So now, in the red triangle, which is actually what I'm trying to solve for, the way I'm going to find angle B prime, since the angle here in the red triangle and the angle that's 72.2 form a straight angle, they must add up to 180. So B prime is going to be 180 minus 72.2 degrees. So B prime ends up being 107.8. To find little angle C prime up here, I'm using the three angles and subtracting the two I know from 180, which gives me 14.2. Now to find little c, I'm going to use the law of sines again and set up the proportion. C over the sine of 14.2 is equal to 11.4 times the sine, or over the sine of 58. I'm going to multiply both sides by the sine of 58. Sorry, multiply by the sine of 14.2 on both sides, not sine of 58 on both sides. C end up equaling then 3.29. And I have solved my second triangle. Here's the red triangle I just solved, and on the previous page you had the bigger triangle here with the three answers there. We will talk a little bit more about that on Monday. Have a good weekend. You may want to watch this more than once, as there was a lot here.